Hello everyone and welcome to Handmade Hero Show, where we code a complete game live on stream. We sketched out a routine yesterday that we want to code today, and I don't know why I'm still wearing my headset. That was for playing Slipways in the pre-stream. If you haven't played Slipways yet, I highly recommend it. You can go to slipways.net and you can get your Slipways on. This is actually for the PC version that's coming. The Pico 8 edition is the one I'm playing because the PC version isn't here yet. But this thing is awesome. It's like my favorite game I've played in quite some time. And quite a respite from playing some Animal Crossing, which is like absolutely the most tedious game that you can imagine. Now, so check out Slipways. I am going today to be doing the routine, the grid-based raycasting routine that we sketched out yesterday, because I wanted to test that, because we want to sort of circle the wagons and finish up the raycasting part of the lighting system, which, works fine as it is currently, but is not up to the speed that I would prefer. So basically, what we need to do is make that run fast enough. And if you take a look right now at, how it's running in game, you can see, oh, wait, you know what? That's running the wrong route there. Grid-based raycast. Don't we have like raycast or grid raycast? That's it. So if we want to, we can switch this back on by saying use 4 arrays. And if we take a look at the lighting, there's two things that we're basically working on right now. So we roughly have the effects we want from our lighting system CPU side right now, but there's two things I want to do. One is reduce the noise in the sampling, and the other is to just speed it up. Now, it does run 30 frames a second pretty solidly right now, but the problem is I'd rather it ran 60 frames a second because we're going to have more complex geometry in here. And so I don't want something that already can't hit 60 when we're not really using the full geometry. And yeah, we could just do this GPU side, and that would probably get us our frame rate back. But, I want to do a CPU side one at least first and prove that that's feasible, because I don't really know how much ray tracing support on cards we're going to be able to count on. Like, it'd be nice to have a fallback plan for if you're running on an iPad or something. Who knows what you want to do. Obviously, I refuse to use Apple hardware now because of their ridiculous policies on not letting programmers distribute programs. They're basically like Richard Stallman's arch enemy or something, for no real reason. Even if he does occasionally eat something from his foot, that is not a reason to not allow people to distribute software on your platform. That's just basically antisocial and weird. Anyway, let's go ahead and take a look at the routine that I sketched out and how it would need to work. So in order to start using this grid raycast routine, we need to do 3 things. First, we need to actually implement the routine correctly. There's a couple things in here that are just sketched out, and we need to fill those in. We can do that now. Then we need to do 2 setup phase things. One is we need to produce the lookup tables for the directions the rays go. And that's not that hard, but it is a little finicky. So we'll have to write that routine. And then the other one is we need to actually grid up our geometry. So we've got 3 steps to produce here. So I'm going to go ahead and comment in the routine we sketched out. And we'll start by trying to make this work sensibly. So if you look at what's going on, the first thing you'll notice is we don't have the walk table here. And so what we need to do here is, in much the same way where we're actually doing the raycasts here, where we pass the ray in, we need to know what our walk table is. And I think that's probably going to be something that comes from the outer code, because my guess is that, if you look at what this is going to do, the people who look up the ray are the people who know what the walk table is. So it's probably going to look something like walk count and we know that this is also a small value. I don't know if we actually need to specify that here, but it's something that would need to, that might affect, like it could be relevant to the optimizer. So I'm just going to tell it that it's a tiny value. And I don't know, sometimes that's actually worse. This is one of those ways that C is just terrible. Like, there's no way to tell it things like, this is an 8-bit value that never overflows. Like, that's the actual information I need to give it. And of course, you can't give it because the C++ Standard Committee is like too busy, you know, going on vacations to theory land without actually ever making the language work. So anyway, I'm going to give the walk table a little setup here, and we're going to assume that this part doesn't actually need to happen, right? So what's actually going to happen here is when we look up the walk table, we're just going to look it up like this. We're going to say like the grid index equals the walk table walk index, and this is the grid index here. And so those are both driven off of this, well, not both. That is driven off of the walk index. So we run through that array in the way that you would expect, and we pull out the individual grid squares that we think that we're going to need. We pull those spatial grid nodes out of this, out of whatever the storage is going to be for those, and we expect each time we get one of those to see a start and a one pass last, right? Now, these are probably just going to be copied directly out because all they are is two 16-bit integers, which is just totally like, it's a 32-bit value, right? So we don't really want to do anything where we actually use pointers or anything on this. So we're just going to copy this out and access it this way. That just lets the compiler know that it's not aliased. Like, it just simplifies things for the optimizer. So now when we go in here, we're going to be loading these leaves out, and each leaf is going to have the information that we require. We have the hit ref color and the hit emission, and those need to come from somewhere. Mostly, I think we're just doing this. And if we look at what's happening here, this is kind of busted, actually. So my streaming machine right now just popped up a thing that says, we've turned on storage sense. To optimize storage usage, we've turned on storage sense for you. That is a terrifying statement, so I'm just going to go over to this machine and see what that means. I think that means we're low on disk space, so I'm going to go ahead and make that not happen, because that is very bad. Whatever it's doing, I don't trust it. Like, if Windows 10 thinks it's doing something, it should stop. It will never be good. It's just a bad situation. So I'm going to go ahead and delete some of these recordings here that were on this machine and like free up some disk space that way so that we do not have this problem. And I'm going to turn off storage sense because storage sense is giving me the creeps. Windows 10 is like the worst thing ever. I really wish... I think John often says the phrase, they need an adult to supervise it, and I totally agree. I don't think Windows has had an adult on the team in like, I mean, at least in management, for an incredibly long time. They may have forgotten what an adult looks like. They're like, oh, an adult, that's the thing in diapers that like waves a rattle around, right? And you're like, no, that's not an adult. That's the opposite of an adult, actually. So, okay, I have cleaned up this particular problem here, and now we can go back to actual programming, which is what I wanted to do before Windows interrupted me. Okay, so going back to actual programming, what I want to do here is I want to make sure that we're actually picking these things properly. And if we're loading these things up 4 at a time, so this is testing 4 leaves at once. You know, one of the other things about this is these are all 4 wide, so these leaves are 4 boxes packed together, but it's fine. We want to be able to load in 4 ref colors at the same time. And we also want to load in for is emissions at the same time. So these need to be loaded this way. Now, these are a little bit piggy. They're bigger than they need to be, but it's okay for now because we haven't done storage optimization on this yet. We're going to have to make sure that we actually get the most performance out of it because we don't really want to be moving a bunch of crap around that doesn't need to get moved, right? It's just worse for the cache and takes more instructions and et cetera, et cetera. So the more things we can load up into one, the better. And so if you looked at like this, for example, so you've got like the min, the max, color, the emission. There's so many things that we could start doing here to optimize the way that these things flow through the pipe. And so eventually we may like do some of that, right? That's all I'm saying. So I think that's all we really need here. This loads everything out that we needed to. We know that these are 16s as well. Like I said, all of these are small, right? And so we can just leave that be, and we can look to see what the compiler is actually generating, and we may need to do other things there. It depends, right? So in here, we now have a question. If I compile that, what I can do too is sketch out what these look like as well, because I might as well do that too. So we would know that if we were going to implement this routine, the grid nodes, we now know what they would look like. They're a start index and a one past last index. And we also know what the leaves look like, so we know what this looks like. We know that this is a boxmin, a box max, and a ref color and emission. So this is for emissions packed. This is for ref colors packed. This is for boxmins, and this is for box maxes. And those can all get load opt here, and these get loaded in and processed here. So that seems totally fine to me, and doesn't super scare me. So if we go into the lighting solution and we look at what we're doing here, so we can also say like, okay, in the same way that we were just gonna like have all these different things flat on top of each other, I can go ahead and grab an array for each of these and say these are gonna go in here, and I don't actually know like what they're gonna look like yet, and I don't care, but we know that we're gonna be loading these off like this. And actually that's spatial grid node, spatial grid leaves. So that's the whole collision detector. Like basically this is the Raycaster now. And you can see why I wanted to try it out this way, because when I was thinking about it in my head, I'm like, this can be so much more straightforward. All it's doing is doing an index-based load off of these leaves, right? So it loads indices in order and loads leaves off of those indices. So it's a dependent load, but there's nothing to predict, right? There's no if statements at all in this entire thing. So you're only paying, the only thing you're paying for during the Raycast is one branch that is only happening at the end. So this is predictable the whole time through until you end, right? And then you've got this one. So this is the only like issue, is the branch for this loop. Otherwise, it's just a straight streaming processor, right? Now, there's issues with it. I don't necessarily know that it's going to be blazingly fast, but you can see why I wanted this, because if you compare this to how complicated like the KD tree or AAB tree walks there's just a lot more decision making going on. And the more decision making there is, the harder it is to make the routine operate in a streamlined fashion, right? Because it's not just a straight stream process that the CPU can chug through, right? And so I don't know what else to do to predict its performance, unfortunately, so we're just implementing it. But that's the idea. That's why I want to test this one. So I think that's everything for the loop. So mostly now it's the support of the loop that is the issue. Now, exiting the loop, we have more work to do, because before we fundamentally have two ways we can raycast. In this version of the raycasting, And this is another reason that I like it, but again, it could end up being a bad idea. But the other reason I like it is instead of casting 4 rays at a time, it casts 1 ray at a time. And normally you would think of that as a bad idea, but the problem is with a Raycaster, when you cast 4 rays at a time, they're incoherent. So you don't necessarily know that they have to that all 4 rays go down the same parts of your spatial partition. So if you're doing it that way, it means every time through your loop, you're testing 1 leaf at a time against 4 rays. You would rather be testing 1 ray against 4 leaves if you can figure out a way to make that fast enough. And in this case, I think maybe we have. I don't actually know. The problem we're going to run into is if you don't have very many leaves that are actually filled with, actually 4. If a lot of the leaves are filled with only 2 or 1, that becomes a problem because then you're spending a lot of time doing operations that you don't use. Much like in the other version, you're spending a lot of time walking down tree branches that aren't necessarily useful for a particular ray. So you can either push into the spatial partition side of things, or you can push into the leaf side of things, that inefficiency, and the question is which one's smarter. Now, there are ways you can actually fill holes, so if you look at what's going on here, there's another way we could write this routine, and again, it may be the better way to write this routine, so we're going to have to write it both ways to see which one's faster, probably. And the other way to write this routine is to pack on demand. So if instead of doing the interleave here, what we actually did was the interleave in a pre-walk, which is the way I first was sort of sketching it out, and I said, well, let's try it this way first. If you actually do the interleave in a pre-walk, then you know you are only paying the absolute minimal wastage because you only waste at the very end. It could be that that's just a fundamentally smarter way to do it. So basically you have a pre-walk that goes through loading in interleaving as many things as the ray actually touches. And again, I really don't know which of those two would be more efficient. So you're going to have to figure that out yourselves, and I'm going to have to figure that out myself as we go. So that part is tough, and I'll slap a to-do in here in case, just so everyone remembers. And so it's hard to say. Now, it's worth noting that this one is still fine when there's nothing. So if there are no actual members, it will just skip, right? So we're not wasting computation in cases where you don't. So we're not wasting computation in cases where there's nothing to do. We're just wasting computation where there's not a multiple of 4 things to do. Because whatever the modulus is, whatever the wastage is on that, if there was only 2 things in it, but we compute 4, then we're wasting 2 lanes of our SIMD. In much the same way that if you went down a branch of a tree that you didn't need, for one of the rays or 2 of the rays in your lanes, but the other 2 did need that branch, then you're wasting half of your lanes in that case, right? So the wastage is very similar in both cases because when you mask out, you're going to end up masking out something and you don't actually need to do it or whatever, right? So it's just, it's the thing that happens with SIMD. It's why SIMD is inefficient. You do it because you can tell the CPU to do a lot of things at once, and that turns out to be a big benefit. But it's inefficient because you can't always come up with enough work to do without going through a lot of gyrations. Especially in things like this where you're trying to cull. All right. So now if we take a look and we look at the outside of the routine when we fall out and we just have to figure out which ray we're actually taking. The fastest way to do this would be using SE3, and use a minpose EPU, which is this right here. And the way that we would do this is basically going to tell us it would put into the min test. It would actually put in there who was the actual minimum value. And that's a much faster way to do this than actually doing any kind of sets of swizzles. The question is, do we want to use SSSC3? We looked it up, and there is nothing, like nobody on Steam doesn't have it. So it's probably pretty safe to use 3 more or less across the board. So we could probably use min-pos EPU, and if we did that, then if you take a look at what that actually does here, so you can see in the Intel Intrinsics guide, min-pos EPU. So if you look at the way this behaves, it's basically a horizontal compare. It takes 4 cycles to do. You can see why it's SSSE3. It's only in Skylake and forward cores. So if you have the old ones, it's not there, I guess. Now, sometimes the Intel Intrinsics Guide is wrong. I mean, how could it be right? It's only made by the people who make the chips. So sometimes you want to go look at a third party for that. So I don't actually know. The Steam hardware survey is really the thing, but let's take a look at whatever that is. And what's that instruction? It's that. So if we turn on SSE, we can look here and see what it actually thinks it's on. So in this case, it's just register to register. We don't care about register to memory. Here it is. And you can see that it's in Skylake, Ice Lake, Kaby Lake, Coffee Lake. And okay, so basically the Intel Intrinsics Guide is full of it. This is totally wrong. I mean, here it is. Like, it's on everything. Like, so I don't know where they were getting that from. Like Sandy Bridge, Ivy Bridge, Haswell, Broadwell, like everybody has it way before Skylake. So I don't know what I don't know why that's the case. So we can do that. It's a latency 4 instruction. So to be honest, I'm not 100% certain we actually need it, because if you take a look at how long it takes us to do it the other way around, it's also going to be for probably latency 4. I mean, it's more like latency 5 to do it the other. So I'm going to go ahead and say this is just stupid. Like, if it's a latency 4 instruction, but it only took us 5 instructions probably to do this, I'm not sure we actually need to do that. I mean, I guess the benefit is this gives us something better to work with. I mean, I guess the benefit of it is it's latency 4, but it puts the right thing in there. And I didn't really have a good strategy for putting the right thing in there. Like, we needed to use a shuffle table to pick up what the answer was. And so I suppose that the argument there is like, look, it's latency 4, but it puts exactly the right thing in for us, I believe. Because if we take a look at what the actual result is of that, you can see that you get in 0 to, like right here, in the 0-2 bits, you get the index of who was the minimum, right? So it looks at all the 16-bit integers, of which there should be 8, right? And it fills, oh, big stretch. It fills the bottom 3 bits with that information. Although, what the heck is the min? What? Where do those go? Oh, I'm like, what the heck? It's just using those as temporary variables for some reason. So it's storing the minimum, the value that was actually the minimum, it's storing it in 0 through 15. And then in 16 through 18, so in the next 16-bit up, it's storing the index, right? So if we actually wanted to use a byte shuffle, we'd have to do like a replicate that, like, you know, that broadcasts this thing across the entire selection. And that's fine. So if you look at where this is being placed, it's kind of a little bit inconvenient. So we would need to do a shift first to move it down. So it would be something like this. Like, you'd do a shift, or well, you could do a shuffle as well. So you would do a 32-bit shift, or I don't know, do they have a 32-bit shift? They may not. No, they do. I was like, I couldn't remember if 32-bit shift got added the first time or whether 32-bit shifts were added later. So we can do a shift right, and I want that one. So we can do a shift right by 16. So it'd be like a sray EPI 32, right? And what we would want to do here is just say, like, okay, we want to shift this thing after we get it. We want to shift this thing right by 16 to put it in the bottom. And then we want to do, so that produces a new whole ball of wax there. Then we want to do, now that we have that, we want to do an shuffle to broadcast it, right? And you can see, so this avoids actually loading in a table, and which, again, this might be faster. I mean, just looking at it, I'm wondering, because I don't know how long move mask takes. I don't know how long move mask takes. It's not long, right? So yeah, I mean, it may just be that it just isn't worth it. You just move mask and load auto shuffle table. I mean, seems like it. So even though we could use that, and what's shuffle EPI 8? SSE 3. So if we want to use that, we do have to use SSE 3 as well. So we don't actually get that for free. If I look at UOPS info, what's PShuffB listed as in terms of architectures here? If I go to just the standard register shuffle. So, again, are they sure? I don't know. I don't always know if this thing is right. Anyway, doesn't really matter. Point being, that's probably fine because there's not going to be, again, like I think min pause and shuffle are both fine. So it's really hard. I mean, PShuffB, not regular shuff PS. Regular shuff PS goes back even further. That's like to the first. That was in the first SSE release, like SSE 1. So I don't actually know what to do here. I do not know which of these would be smarter, but it does seem like you'd be doing a lot to, once you actually got the min out there and you want to then produce a shuffle that corresponds, in order to shuffle any shuffle you can do that's going to have an input is going to be SSSE3 anyway, so you're already kind of out of luck. Because the inputs, I don't think you can... There's nothing you can do. There's nothing you can do that that doesn't use an immediate, right? So basically, the first time, like PShuffB is the first time you can actually get something out. Like, as far as I know, I don't think there's any other way besides PShuffB to have something that's in the register and actually do something with it, right? Everything else that shuffles is an immediate shuffle. That's what I recall anyway. So yeah, so having to do all that work, it seems like maybe you just load the shuffle table and call it a day, and that way you don't really care about min pose, because it just seems like it's more trouble than it's worth to get that out. Now we could use it instead of doing it this way. We could still use min pause EPU and say, look, we do the mul, we do the min pause, and then we're just gonna actually like move that 32-bit value out. So we'll just extract the 30-bit value and then still use a shuffle table. And that may still be faster than doing all of these. It's latency 4, but it might work. Maybe. Again, it builds up a huge dependency chain off of here, so I'm not sure. But yeah, so if we did a min pause here, and then we said, look, just move that value out. So, you know, maybe you do the shift so that now you've cleared it, and then you do an mm convert. and we just extract the value. So in fact, actually, we may be able to do that in one go. Actually, we can. So what we could do is not do that. We could just say, all right, do an extract EPI 16, and then just say, look, we need the second one, bro, right? So like get us that particular one out. So this here is whatever the actual lookup in the shuffle table is. So this is the like shuffle index. Here we would just say, all right, that's the extraction that we actually wanted. And now we just say, look that up in the shuffle table. And off we go. So once we have that, that just loads a shuffle table for 0, 1, 2, or 3, right? Whichever one it's going to be. And then we shuffle we pshuff B. I don't know why they insist on always having different names for the intrinsics versus the instructions. It's maddening. Just call it something. If it's shuffle, call it shuffle. If it's pshuff B, call it pshuff B. Just like this, nobody wants this. I do not know why anyone wants this. I should just make a giant pound define thing that like, but you can't even do that because they force you to pass these different things. I hate this. Just make it look like assembly language. It is assembly language. So frustrating. And the typing, like the MM128 versus 128, I hate that stuff. So annoying. Anyway. So what we want to do here is we want to go in and make this code path now be correct. So we want to shuffle everything so that we load up a shuffle table. We shuffle each time to produce a output that has only the one ray we care about, right? Now, because there's no reason for us to drop to scalar here, even though we only care about the thing that's in the 0 column, because so actually we don't need to do this either. This can be an like load 1, now that I think about it. So we can actually just load a single value. I don't know what they call that in, oops, where's my, here we go. So if I want to load just one thing, you gonna let me do that? You're not. I feel like there's a way to do a load 1 PS of a float. So shouldn't there be a way to do a load 1 of an int, right? But if I remember correctly, there's some really weird thing where loading one integer actually just doesn't work. And the intrinsics like don't work on, they only work on Windows or something. I don't remember the specifics. It's absolutely nuts. It's again just more stupidity. But like I want to say there was a thing that like you can do, was it in conversion? It's also frustrating. So yeah, it's like I don't know where it is. I do not know where it is. There was a way to like cast from an int to one of these things. Yeah, set one. So I want to say that there was some really weird stuff where when you do a set one like EPI 16 or whatever, it like doesn't work like on Intel or some weird thing like this. I really cannot remember the specifics, but it's like, I mean, it doesn't work on Linux rather. There was some ridiculous, like getting the VP broadcast W like didn't happen or something. I just cannot remember. So what we want to do is this, basically. We want to do a VP broadcast D. And we want to do a VP broadcastee of 0123, right? So we would load that up and we would put that in there. So it just goes 0123, 0123, 0123, but it's not actually 0123. It's whatever the actual indices are. So it might be 4567, 4567, 4567, 4567. It's just pulling the correct bytes so that everyone shuffles into the lower lane. That's all we're trying to do here, right? So I don't know if I can actually use this on Linux. I just don't remember. I remember there being some weird thing, like I shipped a version of Meow Hash with this in it, and people were like, it doesn't compile on Linux. And they were right. It didn't. And it was like, what the heck? You know what? I can test it here, because I don't really want to go the Stack Exchange route and have someone tell me something wrong. So let's just test it here. Here's GCC. I'm going to shove this in here. And just see what it says if I include the intrinsics file. So in here, if I set the options, I'm going to use Clang because I don't really actually know how to use GCC. I haven't used it in a really long time. I assume the switches are the same. They usually are, but I don't actually know. So if I go to Clang here and I say, all right, like go ahead and include like, what is it, intrin.h or something like this. Intrin.h is not correct. Is it this? It might be that. I'm going to go ahead and look at Meow Hash. Because I don't ever remember what the heck. The fact that these are different include files on different platforms is also amazing to me. Everything about the way these intrinsics were handled is amazing to me. It's like the biggest cluster of stuff for no reason, like at all. Like everything should have been done cleanly here, and none of it was. All right. So if I do that, it does not like that. Now maybe that's because what's the architecture switch on this thing? So I'm going to give it like a boost and say, look, use all the extensions and all that stuff. Do you know this instruction? So yeah, so unless I'm missing something, oh no, it's fine. So it just didn't, because I didn't give it a number. All right. So it looks like I can use set EPI 32 on Clang. So I'm going to go ahead and say it was just something else I was thinking of, and we're okay. I just want to make sure that I wasn't going to set a little booby trap for folks compiling on another platform there. So set one EPI 32 should work, and that does a broadcast, correct? Like I'll verify that it actually does a broadcast, but then I'm going to say like that's the way we'll just load out of our table. So let me look at the vBroadcast. VP broadcast, right? No? Where's the broadcast instruction? What? So what is this actually doing? You notice it doesn't actually mention. What does it actually do? Why does it normally it has the instruction that it's going to use, and in here it does not, which, oh, here it is. So VP broadcast D, VP broadcast W, and so on. So why was I not able to search for these? Is there a reason for that? Is that because of, like I don't have something checked that I need to? Okay, so those were in AVX. So if that intrinsic might, it says it's in SSE though, so I wonder what will it generate only in SSE? What will it actually use? Would be my question, right? Like if I use that, if it's not gonna do a VP broadcast, what is it gonna do? You know what I mean? Like, because I don't really know what that will actually generate. So I guess one way to do it is just to look and see what it generates. So if I do a set1 API 32, let's just see. Because I don't, again, I'm just nervous. That's all. I'm just nervous about this. But if I do a set1 API 32 off of the shuffle table, like so, that's what I actually want to have happen here. And if we do a nerfing of the rest of the routine, like this, and I don't know, transfer PPS is nothing. Let me just go ahead and make sure this does something. First, and this needs a convert. So if I'm going to do a convert here, I need to do a, so yeah, again, if I do this EPU 16, this is a little bit gnarly, because if I do a convert here to go from float to 16, I have to then pack. And after I pack, the index of which 16s to grab is slightly off. Well, no, it's still correct because it's still 0, 1, 2, 3, 4. Yeah, so, okay, it's fine. So after I do my mul, this puts it into the range. So then I just need to do an convert. And I'm going to do this in actual multiple steps then. I'm going to do this here where I'm going to do like, you know, in T-ray integer, basically. So I'm going to do like a mul, and then I'm going to do a convert EPI PS, right? So this will basically turn these floating point numbers into integers, which is what I want. So once we have them as integers, then I'll do the comparison on them. Now, one thing... So actually, I don't need to do the multiplication, do I? I mean, you sort of do, because we're going to truncate them, so I guess we do. I was going to be like, you can just compare them directly. Because the minimum, like a floating point value... If you compared the floating point value, as if it were an integer, that would work, right? Meaning a floating point value's layout is such that it will compare as if it was a signed integer. Is that not true? Because the sign bit is still the first bit, meaning much like 2's complement, if the high bit of the floating point number is set, it's negative. If it's 0, it's not. Then you have the exponent, and the exponent works exactly the same way. It gets larger as the number gets larger. And then you have the mantissa, which is just an integer, basically, in the exact same way. It just gets larger as it gets larger. So I think that, I mean, I'm assuming if they were smart when they did IEEE, which they were, if I remember correctly, they were very good, they wouldn't have wanted to make 2 comparison circuits. They would have wanted to be able to feed the IEEE floating point value directly into their normal comparison circuit and have that do the comparison, right? They wouldn't have wanted to have made a completely separate comparison circuit just for a floating point number when you wouldn't normally need to. Anyone out there an IEEE expert who wants to confirm that? But that sounds right to me. We probably don't have any IEEE jockeys on the stream right now, but that sounds right to me. Because it seems like they laid it out exactly such that you could have done that. But I'm just not sure about the exponent part. Because when the number is negative, of course, our numbers are never going to be negative. So in our case, even if they didn't do that part, I know I'm right for us. Because in our case, we're never negative. So we don't actually care what they do with the exponent or if there's something special. So I can confirm that I am not an IEEE. Fair enough. In this case, we could. I'm pretty positive we could. Because... So we don't actually need this convert EPIPS at all, I don't think. So, you know, we don't really need to do this. But the reason that I'm going to is because since I have to pack down to 16, that part might break. If you truncate the end of the mantissa, I'm assuming that after the multiply, truncating the end of the mantissa would do what you would do anyway if you were doing the conversion. So I want to say that basically, like, there's two things you could do here. So there's like when we do the minpos EPU 16, there's like the horizontal compare, right? So this is our hcomp vector. And so there's two ways we could do this. One is we can actually convert this to an integer, right? And then we can say build this by doing a pack. And these are unsigned. We know that they're not negative because you can't have t-ray be negative. So if we pack t-ray int like so, where we just pack unsigned 16s as a down convert, I think that's what they normally call this instruction, right? Convert pack 6 integers to 8-bit. No, so it's pack. It's the it's actually the pack 32 one, but where is that one? Okay, I want ones that just have pack in the title, please. I don't actually want you to search the description, but thank you. So here's pack S. I guess you can't pack unsigned. Again, I don't care because this number is the same no matter how you interpret it. So it's pack S EPI 32. And that'll pack these two down to 16s. And then we can run the hcomp on this, right? So this is one way to do it. And if we were to look at it step by step, we would, and we need to do the multiply either way. So I could do this and say, all right, there's an M128, which is like T-ray scaled. And this happens, right? So if we do T-ray scaled and scale to the 16-bit range, and then I do the T-ray scaled convert, if I do the conversion here, you know. And I guess I shouldn't say, I don't know, maybe this doesn't happen in both cases. In fact, maybe it doesn't. So this would be the steps. You scale it, you convert the scaler to 32-bit, you pack the 32-bit value down to 16, and then you compare the 16s, right? The other way to do it is to just say, screw it. I do not fundamentally care about that at all. And you then literally just do a cast, I think. So you need to do a cast, and you need to do a cast and an and to knock out the 16-bit values you don't care about, right? So you do... trying to think if there's any other way. Like, I want it to... do just an extract. So let me just take a look and see what an unpack would do here, because an unpack might be what we want. Right? So in here, if we have like unpacks, unpack high, unpack low. So if I just take the upper part of these, unpack and interleave 60 meters from the high half. So yeah, it's not quite what I want. Because I would want something that actually just zeroed out. So there may be no way to finesse this. Like that may just be fine. It's only 3 instructions. Because I can't think of it. Because although you could do, like, you could literally just compare the bits without, you could let minpos compare the bits. I don't know how to put it into a structure that gets rid of the cruft at the bottom. So I need to compare just the high 16 bits of each 32. So like packing the high 30 bits, the high bits there, I guess is a shuffle. Would a shuffle do that for me? Shuffle 60 inches in the low 64 bits of A. Yeah, that's not what I want. So I don't actually see. So we could do a P-shuff B, right? A P-shuff B would do it. And so, you know, you could do this. You could do like a... You could do this. Where you say, take T-Ray, shuffle it according to my specifications, and then we have the bits arranged that we actually want to compare, right? So it'd be like that. You know what I'm saying? So I think that would be it. What's the problem? Oh, is it P? Yeah. 228I. Wait, what are you saying here? Cannot give our argument 1 from M28 to... no, you define... Okay, so is this actually the other way around? I never remember which way they write these. Yeah, okay. So, yeah. So this probably is wrong too then. This is probably the wrong way around, right? This is probably convert PSE PI32. Yeah. So here's the 2 ways we could do it. One is 1 instruction. It's this instruction. 1 is 3 instructions. So this is just better all the way around, I think. It's just 1 instruction to do everything, I think. And this is a load op, so this would not actually be an instruction. It would just use the address. It'd be a P-shuff B from memory, I think. I don't know if my analysis is 100% correct there, but I'm pretty sure that if you just compare the top 16 bits of 2 floating point numbers, that's the same as first scaling them to the best possible range for the comparison, which is what we were going to do, and then comparing them as doing a conversion. Because the bottom bits of the floating point number are bits that you only get to if all the previous bits were the same. If any of the previous bits differ, you would have already known, because either the exponent was different, in which case the number is higher, or like we already know which one's higher, or the earlier bits in the mantissa were higher. So scaling the number, there's no way we could produce something else. You know what I'm saying? You know what I'm saying to you? You know? Anyone? Anyway. This is where you need some IEEE jockeys on stream. But I'm just saying, I think you can just do this. I think you can just do that, and you're pretty much done. And this here, the HComp shuffler, is just a predefined value that we need to do, right? And so in this case, it's a U8 pattern that we define for loading stuff. And in here, we just pretend that it's an M128i, even though it's not, right? So we just say, look, this is an HComp shuffler. We need this to be decal spec aligned because the compiler is stupid and sucks. Well, it's not actually that. It's actually not the compiler stupid. It's that Intel was stupid and sucks because they made it fault on an unaligned memory operand if you don't put a V prefix in front of the instruction for no reason. I don't know why they did that. It was a very bad idea. Maybe there was a good chip reason, but I seriously doubt it. Anyway, so in here, we're going to basically say, look, we've got a HComp shuffler, and what we need to do is we need to put the things into 16-bit values as necessary. So what we want to do is we want these to go in the correct order. So like 0, this is... That's a null shuffle, right? So this is a thing that would take a register, one SSE register, 16 wide bytes, right? And it would shuffle it to be itself because it puts the 0 byte at 0, the 1 byte at 1, the 2 byte at 2, the 3 byte at 3, the 4 byte at 4, right? So what I want to do is I want to take the high 16 bits of each 32-bit value and I want to put them into 0, 1, 2, 3. And then everything else I want to be 0, right? So if we just look at, what that would look like if we actually try to do it here, manually moving these things around, what that's going to look like is, first of all right, so the high of a 32-bit is 2, 3, right? So I want to put the 2, 3 first, right? So I want to put the 2 and the 3 here. Then the 4 and the 5, again, are not what I want. I want the 6 and the 7. The 8 and the 9 are not what I want. I want the 10 and the 11. And then the 12 and the 13 are not what I want. I want the 14 and the 15, right? So that would take the high bits of the first D word, the high bits of the second D word, the high bits of the third D word, and the high bits of the fourth D word and pack them 0, 1, 2, 3 in terms of 16-bit values. Up here, we end up with stuff that we do not want to compare against this. We don't want any of this to ever be the highest value, right? So what I want to do there is I want to say, okay, we do have a special out condition, which is that you can see here if any of the bits, you can see here, when we do the shuffle, assuming that the index itself is from 0 to 16, then it will actually do a move of that element. But if instead you set the high bit, right? So the 7th bit of the value, if that's set, then you pack a 0. So what we can do is just like say, all right, there's going to be just like clearing that happens. So that we will, in one instruction, literally one instruction, we will both move all the comparison data to the right location, we will zero out everything that's above us, and then we will be prepared to do our min pause. So one instruction does everything. Right? And that's better than 3 instructions. It's not always better than 3 instructions. You'd have to see what those instructions take. But I happen to know that those instructions don't execute in less than 1 cycle altogether. So, right. So anyway, if we look at what happens here, I think that's the complete version of the compare. And the only question I have here... is this the right number of things? It is. This is actually looks like a full-on reinterpret cast for some reason. And the rest, I think we're good. So now we do a min pause, then we extract, and that gives us the index we actually need. Why is this complaining into U16? Okay, fine. you're saying this is an int that you're giving me back. That's fine. And then we have the shuffle table here. So now we just need our actual shuffle table, and then we can have the correct shuffler. So the shuffle table is just going to be this thing again. And when this comes out, the thing that I don't want to have happen is, what if all of the rays all hit something at 0? I shouldn't say all of the rays. What if all of the leaves all somehow hit something at 0? So everything is 0. I don't know what this will pick. Right? Oh, and you know what? That's not quite right. Making those all 0 means they'll always get picked. So I actually need some way of making these be greater, which is tough. So it can't do it all in one instruction, because we need to fill those values with well, we can still do it in one instruction. Yeah, we can. We can sort of do it in one instruction. Depends on how we want to build our table. So we can still do it in one instruction by saying, look, we're just going to repeat. So 0, 1, 2, 3. We will simply pad the end of this thing with zeros. I mean, with element 0. So that way we know if we just pad it out, right? So we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So if we just pad it out with 2, 3, 2, 3, 2, 3, 2, 3, then if 0 is the minimum value, we'll get back 0, because it's never going to compare against itself. Assuming this returns the lowest value, we don't have to do anything else. If it doesn't, we have to add some things to our table in case it picks the later values. Now, I don't know what it's defined to do, so let's take a look. What's going on? How are you not finding that? I thought that was SSE 3. All right, it's SSE 4.1 now. I thought it was SSSE 3. I guess it's not. So yeah, this is so again, it's a little bit more expensive because we don't actually know what our Steam hardware survey would be, or outside the Steam hardware server, we don't really know whether this is good or not, right? Why am I not? No! Valve! All right. So again, we don't really know, and that's why I say, like, we may want to do an alternate path for this. We'll see. But we may just want to say, look, by the time Handmade Hero ships, because, you know, at one weekend's worth of, like, at 4 hours a week, yeah, I mean, come on. SSC 4 will be there. I don't know. We could say that. I'm not sure. Anyway, point being, if we take a look at what this does, I don't actually know which one it picks. So if multiple of these are the same, I'm not sure which one it picks. If you look at the way that they literally wrote this, then that would mean that it would pick an earlier value, meaning it's saying less than, not less than or equal to. So if you pick a min value at 0, and then a later one is equal to that one, it won't overwrite it because it's not going to be less than. It's just going to be equal to. So we would assume that that would be fine, and the shuffle index can, like this, cannot ever be greater than 4. It has to be one of those first 4 because it just repeats itself from then on, right? So that's what the docs say, but we may have to test to make sure that that's like actually true, because who knows, right? So assuming we actually have this right, though, our shuffle table then produces whatever it is that we actually want here. And if we do a set1 EPI 32 on it, it means that we then have another one of these here, right? Which is our shuffle table. And the shuffle table just needs to have the correct values to pick out those bytes. So if we imagine that what we're doing here is picking out the right bytes that go, depending on which one of these we want, we kind of know that, hey, it's just replicated. Each byte is just replicated. You know what I mean? So, well, I need a few more of these here, right? So if 0 was the lowest value, then we would know that we would pick if 0 was the lowest value, then we would just pick all zeros. So we don't really have to do anything for our shuffle table there because it's just going to just replicate all zeros, right? Oh, wait, no. I take that back. That's not true. It needs to replicate 0, 1, 2, 3. So it has to be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, right? So it would have to be across the byte here, it would have to be like 0, so it would be 0, 1, 2, 3, like that, right? Because it's going to load this up, it's going to replicate it 4 wide, and then it's going to use it. So that's going to pull the load D word out of everything. Now, if I wanted to pull the next D word out, then it's 4, 5, 6, 7. If I want to pull the next D word out, it's 8, 9, 10, 11. And if I want to pull the final D word out, it's 12, 13, 14, 15, right? So I think literally all we're doing here is just loading it is what it is. It's just whatever, right? And we don't have to use a broadcast. We could use a direct load here, but I'm not sure that we need to do that. Like, we'll see what it generates. All right, so compiling this code, yeah, this needs to pass some stuff to it. And at the moment, we don't really know what that stuff is going to be. So we're going to stub that out temporarily. In fact, we'll just do this. And then we'll worry about it later. So what I wanted to do here is it probably compiled this out. So I probably can't actually look at it this way. But I wanted to see what instruction it generates or tries to generate from that EPI set. Oh, and you know what I could have done there, actually? I had that God bolt going. I could totally use the God bolt for that. So what did you generate, Mr. Man? So let's suppose I wanted to know what this value was. And, like, I return it or something. Oops. What's the deal? Like, what do you do? So for the set1 EPI 32, it looks like there is no instruction for that, right? Let me turn this off because this is more what I'm interested in, just basic SSE. Yeah. So assuming that I do a set1 EPI 32. It looks like what it's going to do here is 2 mov Ds in a peon pack, and that's not what we want at all. Maybe it does something smarter in 03. I don't know, 03. Forget 03. Let's do 02. So what it actually did there is it actually went ahead and generated the correct table that we would have used, and it did a DQA mov. So that pretty much tells me what I need to know, which is that don't do what I did, right? So what I actually want to do here is I actually just want to do the table, like the full table. So instead of doing that set one, where did that go? Set one. Okay. So instead of this, we actually do want the shuffle table to be like, 4 of 16. It's like a Borg index. And we just want to do like, we just want to build this table so that we've manually replicated it. I don't know why I just did that. And that way we can just do this in one load. It looks like that's the preferable way to do it. And so I guess that's how we're going to do it. Because if that's what the compiler wanted to do anyway, and looking at that, there's no instruction for it, so it seems fine. I actually want a little more spacing between those, just so I can see them a little. Oops. For that very reason. Okay. I could also line these up a little better, just so you can see what the table looks like. So what I want to do here is just, again, have this be preloaded so that way there's no set EPI, and that way getting the shuffler is just a quick case of like loading up whatever one of these you're actually looking for. And I don't know how to tell this thing to align the base of the table, but I'm hoping that will do it. Again, C kind of just always just, well, C++ just kind of sucks. So I want the shuffle table here to just produce one of those values for me, and I basically just want it to turn it into something that I can use there. And that should do it. So I think that's everything for getting the min test done. And so like I said, it's really nice and simple. It's one operation to get the hcomp value, one operation to comp it, one operation to extract it, and then one operation to load it. And so that's a pretty efficient conversion from 4 values to 1. There's probably an even better way if I thought about it longer, but that's not terrible. Like, I'm not going to lose sleep over that, especially since this only happens after you've done all these leaf tests, which should in theory be way more expensive. So hopefully, this will be so efficient as to not be something we actually care about, because that already should be more than enough to keep it under the radar if this turns out to be a good routine. So off we go. And now in here, where we've got the actual processing that has to knock on from that, so I think that basically we just do the same stuff we were doing. So the only difference is, first, we just like make sure that the 0 layer, so when we come through here, right, what we're doing is we're saying, all right, put into the 0 level, like, so in lane 0 of our floats, we want to put the value that actually was the hit. So the whole point of this shuffler was just to get us something that moves everything to the 0 lane so that we actually can use that, right? And it doesn't actually matter when we do that. We can either do it to the input or we can do it to the output. And the question, of course, is when is the most efficient way to actually do that, right? And I have no idea. Actually, yes, I do. Also, that's a U8. I think we can do this even better. So actually, if we just let it compute all 4. So riddle me this, Batman. Once we get here, we know who we're going to extract, right? If we know who we're going to extract, we only have to shuffle the actual people who we care about extracting. And the people that we care about extracting are the emission, the ref color, and the T-ray. Right? And the hit normal. So we could... we could, in theory, defer this down to something else. Let's take a look. So in here, if we have hitbox min and hitbox max, if we look for where those are used, you can see that they're only used here to compute the radius in the center. So actually, like, we just don't need to do any of this probably, right? Like, you could probably just do that. So you do this computation exactly the way that you were doing it before or whatever, right? This doesn't need to get cleared. So we come through here. I don't even know if we're going to need to do this. This may not actually happen. I mean, we may need this shuffle table eventually, but I don't know. So we have the shuffler if we need it, but let's just see if we actually need it. So all of this can just happen. And then the question is, well, we've got scale D, and we want to pick which one of those. Like, we want a particular one of those, which is based on whatever the shuffle index is. And we could shuffle scale D at that point. But let's just identify the places that we need it. So ray origin plus ray D in V3, we only need the T-ray to have been shuffled at that point, right? And furthermore, we actually only really need it to be extracted. So we could do a shuffle extract, because I don't think you can do, there's no way for me to do an extract on an actual, like, non-immediate, right? I thought we verified that, and I'm pretty sure that's true, right? So there's no way to get, when we get an actual value out of here, there's no way to say, here's the value I wanted, and it's in a register, right? That doesn't happen. So you would have to store it and pull it out yourself somehow, right? And I don't know which is faster, whether it's to store it and read it, or whether it's to pull it out using the shuffler. You know what I'm saying? But we'll use the shuffler for now just to see. So if we want to pull out the T-ray, so this is the T-ray scalar. If I want to pull out the T-ray scalar, that's just going to be an extract EPI, no, PS. We're just going to use an extract PS, and we're going to extract the 0 value and the shuffle EPI 8 of T-ray and the shuffler, right? So this would get us whatever the scalar is that's the T-ray. You know what I'm saying? So basically, like, this would get us the scalar value of T-ray. So T-ray scalar, oops, not equal to F32 max. In this case, what you can see here is the transfer PPS when you didn't hit. All of this stuff doesn't have to happen if you can't use it, right? So really, this whole nonsense here can also move inside, because if you didn't hit something, you don't need to do that. So since we already know we have to do an if, or we think we do anyway, to fill in a base color here, that means we could save a ton of work in the cases where the rays don't hit. And that's not something we could have done before because we were dealing with more than one ray. That's kind of compelling as well, right? It's a bonus of this routine. So you can see that that's what we would do here. Unfortunately, this stacks up behind the branch, which is not the best possible thing, but, you know, oh well. And then in here, we're going to do a bunch of stuff. These can all just happen the way that they were happening. And so then the only question is, how does this stuff happen? If we look here, we've already extracted T-ray scalar, so this can happen just fine, right? The probe sample, and honestly, this stuff, we don't even really need the extract because this stuff, yeah, it's a long story. We can talk about all this when we actually look at the routine. We're getting ahead of ourselves. There's a micro optimization that could be happening in here for sure, right? Okay, so for sample ref color, we now have a problem, which is that the sample ref colors came from a packed set, right? But if we actually look at how these are loaded, there's no reason they had to be loaded that way, right? So what we could have done is done RGB emission, and actually loaded them out without the select, I think, right? I mean, with the select, but selecting for a different thing. I'm not explaining this well. Yeah, I don't know. I'm going to leave that for now, and we'll talk about that again also later. So this is fine. This part is the part that now we would have to deal with, which is how the hit normal gets done here. And so we can just say that this is like probe sample n, right? And get rid of this so we can see that a little more clearly. This is something we can just compute. So like that's just something we know how to do, right? Because it's the origin is scalar, rad is scalar, this is scalar. Everything's in scalar, nothing's packed, right? I should say single, not scalar. Everything's in single, not packed there. So really what we're talking about is these emission, if we want to get the emission, that's going to be the same routine here, right? So in getting the emission is just going to be doing that one shuffle. So that's pretty easy to get as well because it's just a single value. And then all the rest of this stuff can just do what it does, right? So I think mostly what we're looking at is this piece of code here is the piece of code that we actually need to do, like that we actually need to make good. What did I screw up here? Oh, great. So I'm going to go ahead and assume there's no way to do a shuffle API 8 that has the right stupid casting. I absolutely hate these intrinsics. They are so terrible. Yeah, so basically like this is we want to call a pshuff b and we don't want it to be, yeah, it's whatever. I'm going to make in our SIMD code, I'm going to make a routine for this because that's going to drive me nuts. So in here, I'm going to do one, and it's going to be one that can shuffle either way, right? So it's like we're going to do one that's I guess we could use our F3. I guess we don't have the int version, but I'm just going to call it like this for now, and we'll figure out how we want to deal with this a little bit later. But I'm going to call this like pshuff b, and it's going to take an M128i that's the shuffle, and the M128 that's the value, and it's going to do the ridiculous dance that you have to do to shuffle. It's so nuts. Where do you see this? So it's one assembly instruction. It's just pshuff b, register, register. That's all you would type in assembly. And like C is supposed to be like a higher level language, and C++ is supposed to be like a higher level language, right? What is higher level about this ridiculous crap that I'm about to have to type, right? So in this case, this is the wrong way around. Like, I just want this, but I had to type all of that, right? Oh, that's not T-ray, that's value and shuffle pattern. Okay. So the higher level language of C++ that's doing such helpful type checking here for me and saving me all of these wonderful errors. I have no idea what they could possibly be because all the errors you get when you do this sort of thing are about lane swizzle patterns and things that you don't understand. It's never because you accidentally treated a floating point value as a 32-bit value when you're programming in SSE. That's absurd, right? But here is the like time savings that I got from C++. Instead of typing this is what I would have typed in assembly language. This is what you had to remember to type in C and C++, right? It's absolutely insane. Like, they constantly say that these things are high-level languages, but they're not. They actually make work for you. If you're actually trying, because like what they're supposed to do, what a high-level language is supposed to do, is provide a more convenient way for you to generate the assembly language you were trying to generate, right? Like, it shouldn't be easier to type the assembly language than it is to type the higher-level language, because at the very least, the higher-level language should have just let me type the assembly language if that was the case. And of course, I can't, because MSVC doesn't even support inline assembler, so I can't even do that if I'd wanted to. But the point is, it should have been as simple as just typing p-b parentheses the two inputs, right? Like, that should have been, the higher language was to save me time. And it doesn't save you time. These higher level languages, they're so bad that they just waste your time instead of saving you time. It's so nuts. It's just so stupid. Anyway, so let me actually get this working here so I can actually type p-b the way that I want to. This is complaining about something. Cannot convert 1 from F3 to X. So yeah, in this case, maybe I'll just do this here, and I'll return this here. Same way, right? So we'll do F3 to 4X results, and this will be, I think I do this, right? That's a value.p. Okay. And so we can now do our p-b, and this will come back. I don't know if we have an extract, like extract 0, extract 1 kind of thing. We should probably add one of those to our little tool here. So we can do m, right? But I guess I don't really like that. So I'm going to do this. I'm going to have a thing for F32. 4x to get the F32 out. That's just like extract 0, right? And you do the value here, and that will just do the extract ps of value.p. So that is how we'll extract stuff. So we'll do like a extract 0. Like so. I think that's all we really need. What is the complaint here? Extract PS conversion from int to... What? Warning, initialization conversion from int to F32. Am I doing something odd? Oh, well, that's not good, but that's separate. extract ps should extract... Am I thinking something weird here? Oh, weird. It returns an integer even though we are extracting a float. Okay. I'm going to do it this way. I feel like that's probably fine to do it this way. I don't actually know. It may be that you want to do it this way just to tell the compiler what's actually going on, but I think I'm going to do the store. I think I'm going to do this. So we're going to do it this way. Like so. And that way we'll just say, look, store this thing here, and hopefully the compiler's smart enough to know what that is. You know what I'm saying? Okay. So at that point, let's see. So we have, there's actually a scalar ray direction here. So there's a ray d scalar. Let me call this ray d scalar. Or ray d single, I guess. And then we'll call this T-ray single, because I realize it's kind of just calling it things scalar is wrong because they're scalar everywhere. It's not what I really mean. All right, so we've got our singles there. And I think that's everything. What's the ray origin? So the ray origin we also need the single version of, so I'm going to go ahead and have that come in that way too as ray origin single. And I'm going to do the same replication process we did on it before. So I'm going to say, you know, ray origin equals v3 4x, ray origin single. So yeah. So I'm not sure what we want to do now, but basically this part here where we generate like the normals and stuff like that is mostly what we need now. As far as extraction is concerned, again, I'm not exactly sure how we want to do this, but let me do this pchef b here. So there's definitely some open questions there. Let me see. So we need the diffuse atlas here, which we forgot to pass. I deleted it because thinking that we weren't going to use it, but we are going to use it because we need that for sampling. So let's drop that bad boy in here. All right. So we're real close to being done with how this routine actually walks. And if we look through this part, all we really have to think about now is how we're actually gonna, I don't know, where did unscaled D go? We got rid of unscaled D accidentally. It's just it's the probe sample P subtracting from the center, but you know, oh well. So if we look at this, the other thing I'm thinking is now, maybe I'm wrong. Maybe origin single and T-ray single, maybe, I'm sorry, and this stuff, maybe we don't actually care about that at all. And actually, we can just do this whole thing without converting down, because if you look at where this will actually be used, it's in unscaled D. That's the only place we would use it. And so we don't actually need to shuffle any of those, I don't think. So if we wanted to, we could do something here where T-ray just equals pchef b T-ray shuffler. Right? So now we know that T-ray is correct the whole way around. And then if you did this, this probe sample P is now fine for all of this. Well, okay, but you still have to extract it here, right? So you do still have to extract it either way. So I'm not sure how I feel about it. Do we extract first? Do we extract second? It's a tough call, folks. It is a tough call. So there's a ref off times the Handmade product down here. Here's what I want to do. Let's work backwards from what's being computed lighting wise here to get a little bit of a better feeling for how this is actually getting used. Because I want this to be as efficient as possible now that it's actually able to choose, because it doesn't have to do 4 wide, it's actually able to choose when it steps down. So let's suppose we missed, right? If we missed, then really all we need is the emission direction to figure out how much moonlight would shine onto this. Like, we need the cosine attenuation on the moonlight. But that's it, right? So And furthermore, if we don't actually need to do that work because we know what that value would be, it's the attenuation on the moonlight from... Well, actually, wait, but this is also wrong. I mean, I guess it's not wrong because we are pretending there's a moon that's shining down and we're just like losing some of the light as we bend away from it. So I guess that's fine. No. So it is the emission direction times the moon light. I guess as it comes this way, you'd be hitting it less. So this is just a crappy way of saying, do you hit the moon? Or the atmosphere, right? So I suppose that's all fine. And yeah, this could just be pre-computed as well. So like this is just true for like this whole equation is just a known thing that you just always know for a given ray direction. So you could even pull this up out of like that scalar could just be pulled directly out. So it doesn't even need to be there. I'm going to actually change the way this works a little bit and say, look, let's just do this as like an input value kind of a thing. And maybe what we say here is maybe we say something like that this updates the transfer PPS value or something. So like... you know, maybe it looks a little bit more like this. So the moon color and moonder are not in here. And this value, that the transfer PPS value that we initialize to, I think what we want to do is say that that comes from externally, right? Because that makes a lot more sense. And so in here, maybe what we do is we do something like this. And we say, all right, so we've got a transfer PPS of 4. And actually, these are just going to be things that are like return values of the thing, right? I'm sorry, our output parameters of the thing. And we will initialize them to what we want in the case of you didn't hit something. We're going to say what you should get if you didn't hit something, which might be nothing, or it might be the moon, right? And then I'm going to say, okay, moon contrib just goes in here for now, or something like that, right? And then we overwrite it. The grid raycast does, if it wants to. So basically, it's more like a conditional move that just like overwrites things as necessary. So it's like, here's the, you know, transfer PPS value that's going to write. So when it comes through here, it's going to say, look, I may write that value, and that's where we actually do anything. Otherwise, we just don't touch it, right? And we're not gonna return anything at all. Okay? So that seems sane. So that means like this is what we're looking at here. So what we have to figure out is what are we actually doing in terms of emission and all this sort of stuff, right? So when we compute the voxel irradiance at a particular location, and that's like where we actually hit, the question is, do we actually want to do... This is very expensive. Oops. And since we only have to do it for one... Like, we're only doing one ray at a time across multiple stuff here. Presumably what we would want to do is actually just test to see whether this thing is emissive or not. And if it's emissive... Because if it's emissive, it presumably doesn't also reflect light. But maybe the answer is it does. Maybe it's reflective and emissive. Like, we want to have both. So, I don't know. But let's say that was the case. So let's say emission is in here. And you can see, like, as the emission gets higher, the probe gets lower, which doesn't make any sense because emission should just be added, right? Like, I don't know that we actually want that either. I guess the problem that we have is the way that we do the system. If light's reflected light back from the things when they hit, the problem is we're going to have that the lights will feed back on themselves, right? Because it doesn't know that the lighting from the probe directly under the light source was actually just getting all of its light from the light source. So I guess what we need to do here is actually, we probably just want these things to either be emissive or not. Like, I don't feel like the way we're doing our lighting would allow us to do a surface that was partially emissive and partially reflective. I could just be not thinking about it correctly, but that seems to be true. So I guess what you could do, though, is instead of adding the emissions together, you could just min the emissions. Or max the emissions, rather. So I guess that's what you would do. You would allow lights to reflect light. But you would also, at the same time, you would make sure that in addition to the emission value and the reflected value, rather than adding them together, you just take whichever one is maximum of each channel. And that would allow you to put light into the system and also reflect light at the same time without feeding back on yourself, because at most you'll always ever contribute up to your maximum. That seems right. So I think what we would want here is if this thing is saying, look, here's the emission level of this thing, then what you want to do is say, what's the actual emission that you're actually building, right? So you're building emission times your sample ref color, right? And then that's the channel that you have, right? So you have your emission color is your emission times your ref color, right? And then your sample, right, is... This is your reflect color. So you're reflecting this, and you're emitting this. And then you just want those two things to be like you want to take the maximum of each one of those, right? Yeah. So I think that's good. And this here, where we have the clamp, that ref fall off is still there. So this value is just, it's really just reflect color times equals reflect fall off. Right. So you build up your emission color this way, your reflection color this way. You figure out what the fall off is, and you modulate by the fall off. Now you take the actual transfer PPS and this. So there we go. Okay, so the emission is off the ref color. The reflect fall off comes on here too. We probably could do something where this actually gets handled a little bit cleaner, but let's suppose it looks like that for now. And then the transfer PPS is just going to be like an RG be max, right? So this is going to be like something like this. So I think that's what we want, right? I think that's what we want. That all seems good to me. So that'll write to the transfer PPS RG and B, and it'll write out whatever the maximum is. We want to make sure this is actually going to use a max PS instruction and not ifs. So we're going to have to do, like, as we, as we go through here, we'll as we clean up the assembly that the compiler generates, we're going to have to make sure we give it the right foof to do that. But everything else seems fine. The ref color extraction now, so this part here is a part we actually care about. If we look at sample ref color, get component rather, that's not particularly compelling, so we probably don't want to do it that way. We probably want to do it the way we were doing it before. So we'd basically do like this. And this is probably not the best way to do it. We'll have to think about that. But I think for now, that's what we've got to work with. Right? Okay, so these are all still not done yet. We get down here, the ref, this is the wrong thing. It's just called ref color. Or I guess this is the hit. This is the hit color. The surface color. I don't know what we call that, really. And so then we just really need to focus on how we're going to get like the normal out of this thing, which is again pretty tough. I don't know what max is talking about here. So those are V3s. So maybe maximum is what we need there, but we really just want, so if you look at max here, I guess that's actually the routine we want. Right. The V34X, I mean, F324X, there's a max on that, right? Somewhere in here. I assume. Yeah. So this is the routine we actually want. We want to do the max PSs on these things, but I guess we can't do that right now because we don't really have a way of actually telling it, look, please do that for us. Again, we could just keep all of this in F32X the entire way through, and then you just don't do the extract. I suppose that's fine. Let's just try that. So if we did hit color here, so we did V34X, then what we would do is we would just say, okay, just store the pshuff of this thing, right? And we could also make a pshuff B that pshuffs this whole thing, but that's fine the way we're doing it here. So we'd pshuff B to make sure the RGB now in 0 is the one we actually want. Although as I'm saying that, now that I think about it, you don't even have to do that. Why did I do that? I don't know why I did that. We literally don't care about that. That's just dumb. So hit ref color is actually just all you need to do. So you just do, okay, the emission color is the hit ref color times the emission. The reflection color comes back here, and you would just load up that out into 4x's. The emission you'd leave, right? So that's just hit emission, actually. And then when you come through here and you want to build the emission color, it's just the hit emission times the hit ref color, right? So you don't actually have to extract. You come down here and we need to do the reflect part, but then when you get to here, you just say, look, when we're going to return the transfer PPS is just one color value. What we want to do is take the maximum value and then extract just the bottom. So this would just be like, you know, emission color, reflect color. So there's the transfer color, and then we would just do the p-shuff-b on transfer color, right? So you wouldn't bother ever extract anything because you don't get anything from that. So you just do it at the latest possible time that you could. That seems to be the same thing. So this would be an extract 0 all the way down on the p-shuff-b of transfer color, right? So that way, I think this just does everything you need it to do, and the only problem you have is that reflect color at that point is not wide. So if you made it wide, and we then say, okay, the reflect color, although it looks like, so you're gonna have to do this in single because probe sample n already had to be extracted, so you don't really care about that. So once you get reflect fall off, reflect color, how to mark, you might as well just wait and do it here, right? So you might as well just do like this. And I think that's what we need. Okay, so what else? This is just with shuffler. And then I think we're back to what I said before. So hit color in this case. Okay, so the Hadamard product here has to be done after, right? Because the hit color is never extracted. So we would want that to be Hadamarded in there. Now, the hit ref color, so we could actually do that at the end though. So we don't, because the hit ref color gets multiplied in either case, whether it's emission or otherwise, I think you could just save that Hadamard product till the end. Right? So if you take hit ret color and you look at where, you know, the two places it would be used is here and here. You know what I mean? If you did that at the end, so you actually said that you don't do this, you do it here. Then what you'd be doing is you'd actually be just taking the emission. So you could just, I'm not sure if I'm right about this. So you could do all of this, I think, and just do the Hadamard product at the end. So it would just be the multiplies, like you could just do it by only actually extracting just the emission. I think that's right. I'm not entirely sure. Let's take a look. So in emission color here where we do hit emission times hit ref color. So what I would need to do is say, look, the emission value is actually just going to be a value that we do a max with to max against the reflect color, right? And it feels like you could just do this. Like if we loaded this in a packed value, we could do this directly, right? So let's suppose that you imagined that the reflect color was actually came back as like suppose we did something where the reflect color we actually packed up. So we did an F32 4x of this thing, and we packed up foo. So we imagine we grab that as a reflect color, right? Then we imagine we take the emission color, or reflect level and emission level. We generate this just from the extract 0 of the emission. So we extract 0 the emission, and we replicate it. Now, actually, we don't extract it. We just p-shuff-b it, right? Because if we p-shuff-b the hit emission with shuffler, it's now got emission in all 4. So this is the RGB blah, the RGB blank, and this is the emission, emission, emission. We can then do one max on those, right? Yeah. Yep. So let's say we do the reflect fall off here, and we do reflect color foo times equals reflect fall off. Like so. Then we do the load up. Then we do the max here. And then we just know how much we're transmitting with our hit ref color. So then we say, all right, that's the transmission level for RGB. Now we just extract 0, 1, 2, and go. Although I don't know if we should try to do something different there with the hit ref color. Maybe we just do that. It's in the wrong lanes is the problem there, right? So yeah, you can't really, you can do the max efficiently, but you can't cheat and do what I'm doing here. You'd have to do like a replicate out, right? So that does not actually help you. So we don't care about that. We don't care about this. We don't care about that. This is our actual transmission level here. And so then you just do like extract 0 of this. 1, 2. I think that's it. All right. So you have one extraction that you have to do for each color channel, the RG and the B. And then you have to figure out how to get the normal and the position out. And so I think that means this does look like this. Right? Probably. Although I don't know because this also has to happen that way. So I'm not sure. It may be that you extract that out. I don't know. So that's kind of an open question. Those are kind of an open question. But I think this stuff is now correct. So if I go to extract 0 and I just make a couple of these. I'm not sure how to actually ask this thing to store later values because, like I said, it for whatever reason doesn't seem to want to store anything other than Oh wait, this is not what we want. So store 1's actually a replicating store, which is not at all what I want. I just want to convert. I just want to take a float out of this thing. Here it is. This is what I actually want. I want convert SSF32. That's what I actually want. Now, like I said, I'm not sure about this one because I don't know how to get anything else out of this thing. And it may be that there is no real efficient way to actually do that. We could look, but I doubt it, right? Because that's like, looks like the only one that you get, right? So I could extract an int. So because there was the extract with an immediate that was out here. So we could extract an integer from it and convert that back to a float. Because you can see that it's not doing conversion. So it's actually just giving you the float back. It just doesn't return an F32 for some reason. And I have no idea what the reason is. Intel, you want to tell me what the reason is? Do you have an explanation for that? I don't know what their explanation is for that. But so doing a convert SSF32 to pull something out of there. I'm not sure exactly how we would do that for the other values as efficiently as possible. It might be that what you want to do is the extract. If we did that, it would look like this. And then we would do this. So we're just like forcing it to do what we want. I don't actually know if that'll work, but oops. But we'll see. So I would say the reasonable progress. This is a pretty tricky thing to get right because we've got sort of scalar and non-scalar mixed together. It's always that point. Like when you upshift to packed and then downshift to scalar, those are always the hardest parts of your routines. So I think all we really need to do now is to finish that part off. I can if zero this out for now and do a Q&A. And next weekend we'll focus on finishing that part, testing, and then we'll move on. Oh, and this is no longer relevant because I actually did make sure the max happens there. Again, it's starting to look very clean now, and I don't know, like, but except for this, which is very expensive, obviously, I feel like we're able to trim a lot of the fat out of here. And the downshift is still a little janky, but at least it's like, it's not as horrible as it could be. These don't need to be here. And this is just kind of placeholder for now, but it's these. Yeah, nope. Okay. So in terms of what we need to pass the grid Raycast, I think that's the end to just tie this off. It's work, it's diffuse atlas, ray origin single. What is the ray origin code here? Is that a thing that we know? It's not. So we would have to do a get component on that as well. Boy, I hope this works out. If this actually turns out to be a good way to raycast, it's going to be so nice because so much code will go away. We can just delete like most of all this stuff that we've been using to try and figure out what would be the efficient way to do it. And when we actually hit upon one, it's going to feel pretty nice to clean everything up. This doesn't return a value anymore. All right, let's do brief Q&A here. John said you had opinions on signed and unsigned. You said maybe it's the wrong complication to have. Yeah, I mean, I guess my problem with almost all high-level languages is that rather than making decisions that always save you time, they tend to make decisions that only save you time if you happen to program exactly this one way, and any other way you might try to program, it just falls apart. Which, you know, is the nature of compressing things down for sure, but it seems like it's unnecessary in a lot of cases. So the example in this case would be that signed and unsigned arithmetic is exactly the same in most places. If you add two numbers together, your CPU just adds them together. It doesn't care whether they're signed or unsigned. So calling things signed or unsigned is not a type. What it is a default. So I would prefer if what you said was 32-bit integer, and I'm not going to tell you whether it's signed or unsigned. All that would do is generate code where anytime you did something that actually did need to know, it said, please specify which operation you want, right? So if you then did something like a shift, you could say, do you want an arithmetic or a logical shift? Normally what happens is it uses the signed type to tell it which one to do. I don't want that most of the time. I want to tell you which shift to do. Because just because the value is signed or unsigned, that's like suggesting that there's not values that take on both characteristics, and that's wrong. When you're actually programming, they're fungible. I might do something in a way that it appears like the value is signed for 3 instructions and then change to unsigned to start things later. So it's just signed and unsigned is not right. It's not a property of a piece of data. Signed and unsigned is a property of an operation. And so I think the abstraction that's made in all high-level languages is wrong. I don't think they did it properly. Are you familiar with Home Assistant? No, I am not. Are there alternatives to inline assembly other than intrinsics? Just external assembly, right? You write a function. Like we could write this grid raycast function in assembly language and then link it in. And that is what you do if you fail. Like what you normally do is you try to get the compiler to do something not stupid with your code when you're optimizing a routine. And if you fail, like if you just can't get the compiler to emit what you want, then you just write it in assembly and link it in. That's what you do. Most of the time you can sort of fuss with the phrasing and get the compiler to eventually do it. But if you can't, then you do it in assembly. On episode 300, you mentioned that OpenGL is much closer to a good graphs API than something like Vulkan. I was wondering if other developers you know agree with you on this, and if so, then why would something like Vulkan get support? Who exactly makes the design adoption decisions for these kinds of technologies? Do developers have any say? So first of all, I guess what I would say is Vulkan doesn't have much support. Like, it's just not very popular, right? So I wouldn't say people are supporting Vulkan. But in terms of people who do support Vulkan, the reason is because what else are they going to use, right? OpenGL 4.5 isn't well supported at all, right? So it's more about a decision of what the IHVs choose to give us, and they chose to give us Vulkan. It's a pile of crap, and it's unfortunate, but that's what you get. So when you program on Windows, you get two choices, DX12 or Vulkan. Personally, I'd pick DX12. If you want to pick Vulkan, go right ahead, right? who gets the design adoption decisions? Mostly the IHVs. It's mostly what the IHVs choose. Right? So basically, like, IHVs have to... IHVs are basically who determines everything, more or less. And platform holders can force their hand sometimes. So Apple, for example, can just demand that metal is the thing now, and then the IHVs have to live with it. But short of that, IHVs determine what we get. And they have a fantastically poor track record at producing APIs that are good, stable, and long-term. They're just very bad at that. So... Why is it slow for the CPU to do horizontal SIMD operations? So the reason is because of the way that arithmetic logic units are designed for high speeds. And I guess what I would say is it's not slow. Slow is the wrong term to use. It's latent. Horizontal operations aren't slow. They're just latent, meaning you don't get the results back for a while. They might be very fast, meaning you can do lots of them because you can start many of them. So it's usually a very good idea to be specific. So slow, what does this mean? Well, there's two things you could mean by slow. Slow could mean takes a long time to take input and produce corresponding output. And I prefer not to use that term because it could also mean does few ops per second, like per unit time, right? And slow could be either of these. And the reason that I don't like using the term slow, or if I do use the term slow, I usually mean this slow, is because this slow I can usually program around. So I prefer to say high latency in this case, potentially, because it's not necessarily slow. Because you may be able, if you had many independent ones to do, you might be able to run them at exactly the same speed as something else, right? And so I would say that that's what horizontal ops are. So horizontal equals high latency. It does not mean slow in a can't do many of these per second. You can, they just take a while to get the results out for any individual one, but you can overlap many of them, right? So why are they high latency? Well, they're high latency because this is the way an arithmetic logic unit normally works. An arithmetic logic unit normally looks like this. The input comes in 4 wide lanes, right? The circuit for doing the operation takes a clock. Right? So it comes in here and I've got wiring for each of these operations. And the clock does an operation on each, in one cycle, I'm going to do an operation on each of the lanes, and those lanes are going to feed forward into the next operation, right? So if I have something like a comparison that I need to do, right? Then what's going to happen is when this input comes in, the first thing that's going to happen is the input's going to have to merge crosswise. So the op that I actually have is going to have to take input from 2 sources, right? And so in come my lanes, the first thing is going to be like a feed forward thing that produces, an op like this or something. So like I do something and I forward that result to some other lane, right? And then I do something and I forward that result to some other lane again. Right? And so what ends up happening is if you're thinking about it coming in this fashion, then if you want something that can be answered across all 4 lanes, you have to pay the price of the furthest cascade. So if I need a result from 3 to propagate all the way to result from 1, which is what I need if I'm going to compare all 4 lanes, well, how many hops does it take? Right? Here's 1 cycle, here's 1 cycle, here's 1 cycle, here's 1 cycle. It is 1, 2, 3, and then the 4th operation gives me my answer, right? I mean, I should write this a little bit differently. It should be like the cycle is here, right? The cycle is what moves the thing to the next phase, right? So, and you could also count it as like the input step is a cycle. I mean, I'm not a hardware designer, so I don't know what the right way to write this diagram is. But point being, something comes in on 3, it has to move to 2. Something's on 2, it has to move to 1. Something's on 1, it has to move to 0, and then it moves to the output. That's, 4 cascades. And so when you look up horizontal operations, usually the cycle counts match that cascade pattern really well. So like, for example, if I come up on here and I say, well, what's the actual answer going to be for doing something like the min UPS, sorry, min pose EPU 16. It's like, hey, it's latency 4, exactly what you would expect, right? What happens if I do the horizontal add for dot products with the H add, right? So if you do the horizontal add, you can see that what these do is they do horizontal adds, but they only do 1 step of the add. And you can see the latency is basically like a little less because it doesn't actually have to do all 4. It's not a propagation. It just has to propagate once and then add once and then out, right? So again, you get down to latency 3 because it doesn't actually do the whole add. You have to do 2 of them to add the whole way. Yeah, and you can see like basically all of these kind of line up that way. So again, take that diagram with a grain of salt. I'm not a chip engineer, so like that's probably not a very good explanation of what actually happens, but it's vaguely right. So the point of SIMD is that you have this circuitry that doesn't have crosstalk, and that's why it's fast. It knows it can just do multiplies in lanes, and they're all just stamped copies of scalar multipliers. As soon as you start crosstalking with the lanes, that whole structure breaks down, and you need to have like a bucket brigade that like moves crap around the chip to get it all the way over, and that's what costs. Does that make sense? Wouldn't you use Vulkan for cross-platform? No, it's terrible for cross-platform. Like, why would you use Vulkan for cross-platform? You know that it's not an API you can actually use to write to graphics cards on Mac. And what else do you have for your platforms? You don't have Vulkan on, like, the Xbox. It's not a thing, right? I mean, maybe they do support Vulkan for the new Xbox, I don't know, Scarlet or something. I have no idea. But it's not cross-platform. Like Apple requires that Metal is the driver layer. So if you're running Vulkan on that, it's going through a translation. That's the opposite of what you were trying to do when you wrote to Vulkan, right? Vulkan's supposed to be a bare metal API, and it ain't. And on Windows, it's like, well, all right, so if I'm going to be writing Metal on Mac, I might as well write DX12 on Windows. I ain't going to write Vulkan on like the PS5 and Xbox, whatever they call Scarlet, Xbox One XS12 or whatever the next one is. It just doesn't really make sense. Vulkan is like an API that just has no point in existing. I don't even understand why they bothered. Maybe for Linux. I don't know. All right, looks like the end of the questions. Okay, let's close everything down. All right. Doop, 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 doop. All right. Thank you, everyone, for joining me for this episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code. Maybe you can go finish the grid-based lighting this week while you wait, and that'd be good practice, because I've sketched out all the routines, so the question is just getting them working, right? So you could give that a shot. Until then, we are doing, this is the last week of our Kickstarter. If you want a Meow the Infinite comic, your very own, you can always just click on this banner. That'll take you right there. And we hit basically all of our stretch goals. I guess I don't know, there's one more for a coloring book, but it looks like it'll hit that one too. So you get a whole bunch of cool stuff with it. Definitely check it out if you're into comics or space or cats. That's it for this weekend. I don't know if I'll stream some more slipways. I feel like I don't want to put the pressure on John to like learn to get good at slipways, because, you know, I watched his stream last night playing slipways, and I was like, it looked a lot like Naysale, looked like a lot like Kingdoms and Castles, where it was just a really depressing kingdom that no one wanted to live in. And so like, I'm afraid that his Galactic Empires probably will be that way as well. So, you know, maybe it's best to just not put the pressure on and leave it there. That's fine too. But, you know, if we do want to give some demonstrations about how intergalactic routing is best done, then maybe I'll stream some of that later. I don't know. We'll see. That's it for today. I'll see everyone back here next week at the very least. And I'll go check now to see if John is streaming right now. And if so, we'll rate him. That's it. Take it easy, everybody.